Welcome to Mechanical Drawing and Design N6. Today's presentation is going to be on lubrication of plain bearings. There are two modules on bearings. One is plain bearings and the second one is lubrication of plain bearings. And the module on plain bearings is straightforward, easy to understand, and questions from that module are usually just a direct application of the formula. And so I am not going to make a video on plain bearings alone, but rather my focus is going to be on lubrication of plain bearings. And the reason for that is that usually in your exam, when you get a question on bearings, it's mostly going to be a question on lubrication. Let's begin. So first, let us look at the types of bearings that you need to know for for mechanical drawing and design N6. The first one is the footstep bearings, and these are the equations that associate themselves with footstep bearings. And many of the labels in these equations are things that you already are familiar with, but I may maybe say that FA is the actual force, okay? And also Ft is the tangential force, mu is the friction, of course, and Rf is the mean radius. Now, this is particularly interesting because the mean radius is calculated using either this equation or that equation, depending on whether you are dealing with a situation where you have to assume uniform wear or a situation where you are told to assume uniform pressure, okay? So depending on what your question tells you, you will decide which of these two equations you need to use to find the mean radius, okay? But these equations are the equations that are associated with footstep bearings, okay? You can get the area using this. Capital D is the outer diameter, small d is the inner diameter, okay? And the same thing with capital R and small r. These are the outer and inner radius respectively, okay? And so these are the equations you need to know. And then you have conical footstep bearings, and these will be the equations that are associated with conical footstep bearings. And here I need to point out to you that to get the pressure, you need to divide the normal force by the area and not the actual force, okay, as was the case for footstep bearings. And the normal force is obtained by dividing the actual force by the sine of alpha. This alpha that you see here is the semi-cone angle, okay, in the conical footstep bearing, okay. Alpha is the semi-cone angle. So to find the pressure, you first need to find Fn using that equation, and then you divide Fn by the area. Also, the area here is equal to pi multiplied by the mean diameter and multiplied by the width. And this mean diameter is given by that. Generally, in your question, they will give you what the width is. And of course, you can get the torque due to friction. That is just Ft multiplied by Rf, same as here. And also the power lost to friction is given by that equation there. And I can point out also that the minimum pressure on the surface of the bearing is given by that. The maximum pressure on the surface of the bearing is given by this, okay? Very important. These two are the same equation that you will use here also if you were dealing with a footstep bearing. And the second type, the next type of bearings that we're going to look at is the collar bearings, okay? And the equations associated with collar bearings are these, okay? And these are very similar to the equations for footstep bearings. The only difference here is that the actual force here might be a sum of actual forces, because with collar bearings you will generally have more than one collar. You can have four collars in parallel, and so the actual force will be equal to the total of the actual forces on each of the collars, okay? So if you have four collars and you know the actual force on each collar, then the total actual force will be that force on each collar, that actual force on each collar times 4, okay? So that's how you get the total axial force. So in these equations for the collar bearings, the axial force that you have here, okay, is actually the sum of axial forces on the collars, okay, very, very important. And then you also have journal bearings, and journal bearings have these equations associated with them. And here, the one thing that I may need to point out is that the area, the way you calculate the area is by multiplying the diameter of the bearing by the length of the bearing, okay? Do not do pi by 4 diameter squared. No, this is the projected area of the journal, and it's equal to the diameter multiplied by the length of the bearing, okay? Very important. And so these are the 4 types of bearings that you are expected to know for mechanical drawing and design N6, okay? These are the 4 types of bearings that you need to know. And like I said, there is a very simple chapter to understand in your textbook, which is called plain bearings. Just go through that chapter. You will get familiar with all of these and how to use these equations, okay? And once you are familiar with that, then you will easily be able to navigate the module on lubrication, okay? Very important. Now, let us get into lubrication. So now, first, I will explain to you what lubrication is all about. Now, assume that you have 2 objects like this. Let's say these are 2 metallic objects, okay, used in a mechanical setting. Okay, so you have these 2 objects, and these 2 objects are supposed to rub against each other. Now, let us call the top one 1, object number 1, and the bottom object here, we will call it 2. Now, these 2 objects are working in a mechanical setting, okay, and they're fulfilling some sort of mechanical application where they are supposed to rub against each other. Now, when you look at the objects with the naked eye, their surfaces may seem to be smooth, okay, but in reality, if you zoom it closely enough using a microscope, you will see that the surfaces of rubbing objects are never smooth. So what we are seeing here is a zoomed view of the 2 objects, and we are looking at them at the contact surfaces. And you can see that both object 1 and 2, although with the naked eye they seem to be smooth, but in reality, when you look closely enough, their surfaces are not smooth, okay? And because of that, when these 2 objects will begin to rub against each other, that roughness on the surfaces will cause friction to arise. And with friction, of course, you will have heat and so on and so forth. And now, to be able to manage that situation, what is done usually is that in between the contact surfaces, you will have a fluid that will be allowed to pretty much be in between the contact surfaces. And this fluid is referred to as the lubricant. Now, the lubricant is generally some sort of oil that will have some viscosity, okay? And the function of the lubricant is to reduce the friction between the 2 surfaces. And by reducing friction, what will happen is that the surfaces are not going to wear off very quickly, okay? That is the first function of a lubricant. The second function is to provide a protective barrier against corrosion, okay? The third function of the lubricant is that it improves the longevity of the equipment, because if we can reduce the friction between them, therefore, these objects are going to last longer because they're not going to wear off too quickly. And the fourth function of the lubricant is that it enhances the efficiency of the system. That is just easy to understand, because if you can reduce the amount of friction, of course you will increase the efficiency of the system, okay? And finally, the last 2 functions of the lubricant is that they, first of all, minimize the heat that is generated between the 2 objects that are rubbing against each other. And besides minimizing the heat, they also help to dissipate that heat, okay? So first of all, as the two objects are rubbing against each other, heat will be generated. But if you put a lubricant in between them, the amount of heat that is generated is less. But not only does the lubricant reduce the amount of heat that is generated between two objects that are rubbing against each other, but it also helps to dissipate that heat, okay? That is very, very important. And so these are the functions of a lubricant and why lubricants are important when you are dealing with objects that are coming in contact with each other. Okay, so now let us look at heat. Now, in real life applications, okay, the heat that is generated by two objects that are rubbing against each other is not gonna be completely dissipated through the lubricant, okay? However, in this module, in most cases, we will assume that that is the case, that the heat that is generated is equal to the heat dissipated. Okay, very important to remember that. And now heat generated is given by this equation here. Okay, this you may also remember from power machines and 6. And this equation will give you the heat that is generated in units of joules. Okay. And this heat generated is also the heat that is going to be dissipated. And you can also find the heat generated per second, okay? And whenever you have joules per second, that is actually power. So the power generated can be calculated using this equation here. Now, in this equation, you will see that the mass, we're using the label m bar to refer to the mass in this equation because this is a mass per unit time, okay? Kilograms per second. And because it is kilograms per second, therefore the unit here will be joules per second, or if you want, watts. So it is important to remember whenever you calculate the heat generated or dissipated in units of joules per second, that can be equated to power because joules per second is actually watts. So the power generated here is actually in watts or joules per second, okay? It's the same thing as the heat generated in joules per second. Very, very important. And now let us look at McKee's equation, okay? McKee's equation is an equation that allows you to calculate the friction coefficient, okay? And this is what the equation looks like. Now, when I was introducing to you the different equations that apply to the different kinds of bearings that you can have, mu in those equations was the coefficient of friction. But when we're dealing with lubrication, mu is actually viscosity. The coefficient of friction is represented by the letter F, okay? So McKee's equation allows you to calculate the coefficient of friction, and we use the letter F for the coefficient of friction, and mu in this equation is viscosity, okay? And that you have here is the RPM, P is the pressure, D is the diameter of the shaft, okay, which is also the diameter of the bearing in some instances. And C here is the clearance, and K that you see there is a constant that you will actually read from a graph, but we're gonna get to that. So first, let us look at how you get P, okay, the pressure. The pressure is equal to the load on the bearing divided by the product of the length of the bearing and the diameter of the bearing, okay? So this equation. And the load on the bearing, we usually use the letter W to refer to that. So I could have written here, P is equal to W divided by L times D, okay? So that is P in this equation, it's the pressure, you get it using that equation here. And then you have D over C. Again, D is the diameter and C is the clearance. And this is equal to 1000 if it is not given, okay? If you do not have information regarding the clearance, okay, to allow you to get D over C, then you can just assume that D over C is 1000. Okay, so if you are not given any information for the clearance, okay, usually you will have information for the diameter, but if you are not given information for the clearance, you can assume D over C to be equal to 1000. Okay, so D over C is equal to 1000 if not given the information on the clearance. Very important. And I am going to show you what C is, okay? Because I am referring to it as the clearance, but to be more specific, it's actually the diametric clearance. And the diametric clearance shouldn't be confused with the radial clearance. And I will show you. Okay, so you can look here, you can see these two circles. Okay, in this case, on the left here, both circles have the same center. Okay, but on the right, you can see that both circles are touching, and then you have a distance here. Now, when we are talking of the diametric clearance, it's actually that distance there, okay? If you push both circles in such a way that they touch on one end, the distance that you will have on top here, this is what we will refer to as the diametric clearance, okay? That's C. This C that you have here is the diametric clearance, okay? You can see how it is measured. And what you have on this side, this is what we refer to as the radial clearance, and it is equal actually to C over 2, okay? And this is the radial clearance. So if in your question you are given the radial clearance, remember that what you need in McKee's equation is actually the diametric clearance. So you need to take your radial clearance and multiply it by 2 for you to get the diametric clearance that you're going to use in McKee's equation. Very important. And K here, as I said earlier, this is just a constant that you read from a graph. And this is the graph from which you will read the value of K. And it is dependent on the ratio of the length of the bearing to the diameter of the bearing. So you will take the length of the bearing, you divide that by the diameter of the bearing. That will give you a certain number here, and then you will draw a vertical line until you meet this graph. And when you meet this graph, then you project it on this axis to read which value of K that corresponds to. Okay, very important. Continuing with lubrication and equations, we will now look at Lasche equation, okay? Now, Lasche has two equations, okay? One for the heat that is generated and one for the heat that is dissipated. But like I said to you